All right, so the next periodic trend that we're going to go over is ionization energy. So what is ionization energy? That is the energy in some energy unit, like joule, right? That's an energy unit, required to remove an electron, one electron specifically, in the gaseous state, okay? So there's always going to be a gaseous element we're talking about, and it's the amount of energy required to make a cation. So for example, you take hydrogen, you remove an electron, and then you're going to get positively charged hydrogen ion, right? Hydrogen cation, and you're going to negatively charged electron. That takes a certain amount of energy to split the ion from the electron, right? And in this case, you can measure that, okay? In this case, it's 1,312 kilojoules for every mole of hydrogen, right? So for every 6.022 times 10 to the 23rd hydrogen atoms, it takes 1,312 kilojoules of energy to split it into hydrogen ions and an electron. So that's ionization energy. It's cation formation, okay, in the gas phase. So there's a nice trend on this. The first trend is that the ionization energy decreases as you go down a group. Okay, so as you go down a family, as you go down a column, your ionization energy decreases. So you can see these are different ionization energies, and they're all decreasing, okay, as you go down a group. And why is this? Okay, this is because it's easier to remove electrons that are further from the nucleus, right? So think about for cesium, you're removing an electron to form cesium plus, but it's in that electron, that valence electron's in a 6s orbital. The 6s orbital is very big, right? And so since it's very big, most of the time that electron is pretty far away from the nucleus, the positive charge. So it's far away from the nucleus. It's not going to take as much energy to separate it, separating it out into basically, completely separated, okay? Versus think about hydrogen. That electron is in the 1s orbital, very close to the nucleus, the positively charged nucleus, and thus takes a lot more energy to remove. So you can see that in general, as you go down the periodic table, I think for almost all of these cases, there's a few exceptions, which has to do with some more complications you don't have to worry about. You can see, for example, tin and lead, it doesn't quite work, okay? There's reasons for that, but we don't have to worry about that, okay? The second trend with ionization energy is that it increases moving across the table. And so it's harder to remove electrons with more protons, right? And so that kind of makes sense. So again, if you look going across to the right in general, these numbers get higher. It's not always true. Again, there's some exceptions you don't have to worry about. But generally, it's getting higher as you go to the right on the periodic table. And because there's more protons, same electrons that we're talking about. So this is the same logic for atomic size, why atomic size decreased as we went to the right. Same orbitals, the valence electrons are in the same types of orbitals, right? The same principal quantum number. So they're roughly the same, but you've increased the nuclear charge. And so that makes it harder to remove an electron and form a cation, okay? So ionization energy goes up. So we can practice this, list the following elements in terms of their ionization energy: silicon, fluorine, potassium, magnesium, and sulfur. All right, well, if we look at the periodic table here, all of these are in the same row, okay? So all we have to do is order these from left to right. We can pull up a periodic table here for you. Maybe not. Okay, that's okay. Here's one. Okay, so we're talking about silicon, magnesium, sulfur, right? And there's potassium, okay? And so we're just ordering these left to right, okay? And it's basically as simple as that in fluorine, okay? So the ones that are further to the right, fluorine is the furthest to the right, is going to have the highest energy, ionization energy. There's also second, third, and fourth ionization energies. What we were talking about right there was what's called the first ionization energy. That's just to form from a neutral element to a +1 ion. But you can then define a second ionization energy as +1 going to +2. And then third ionization would be +2 going to +3. Fourth would be +3 going to +4. Okay. And the first thing to notice here is that O is the second ionization energy, takes more energy than the first ionization energy, and the third is always higher than the second. The fourth is always higher than the third, right? And you can go down even to the seventh if you have 7 valence electrons. But so that makes sense because hey, you're just getting a higher charge, right? And like nature doesn't want to be highly charged, okay? Nature wants to be neutral. So the higher charge you go, the more energy it's going to cost, okay? So that's the first trend with these multiple ionization energies. There's also something interesting. You see I've shown the staircase here. And if you look at sodium, there's a huge jump between the first and the second ionization energies. If you look at magnesium, okay, second is higher than the first, but it's not crazy high. But then you go to the third and it's crazy higher than the second. And aluminum, the fourth, is crazy higher than the third, and so on. Silicon, the fifth, is crazy higher than the fourth. So why is that? Okay. Maybe you can think about this. So, this was a practice problem. Aluminum, same idea. Aluminum, the fourth, is crazy higher than the third. And we just explained why, the second would still be higher than the first. The third still would be higher than the second. The fourth would be higher than the third. But why is the fourth so much higher than the third? Well, look, you're going from +3 to +4. Aluminum does not want to be +4. Add aluminum 3+, that's the noble gas configuration, right? We know that aluminum likes to form aluminum, right, is right here. It's going to be, if we remove 3 ions, it's going to have a neon, noble gas electron configuration. So once you remove that fourth electron, you're going into the core electrons. And you don't want to remove the core electrons. That takes a lot of energy. You can do it, but it just takes a lot of energy, okay? For sodium, you remove 1. It's pretty happy because it's like neon. But then you remove 2, the second ionization energy, right? The second ionization energy is the one where it really takes that high jump. All right, so that's pretty much it for ionization energy. And in the next video, we'll continue with the other trends.